Let's take a look at water and how it maintains the temperature here on Earth. Water tends to heat up slowly. Remember, it has a high specific heat. It's 4.184 joules per gram degrees Celsius. So when it heats up, it takes a long time for it to cool down. This is what happens whenever you have a high specific heat, like water does. If you've ever had a pool or known someone who did, they'll fill the pool up and it takes a long time for the water to warm up. Or I would go to our family farm. Again, this is in West Virginia. A river ran through the farm, and we used to go to the river and play. We go swimming in it, and we put our foot in if it were like late May even, and it was really cold. But by the end of summer, the water wouldn't be as cold. It would be a lot warmer. And that's because of the specific heat. Water will absorb slowly the heat from around the atmosphere, around the body of water. And as it slowly absorbs it, the heat, of course, raises the temperature of the water. Remember, the specific heat just measures the amount of heat in joules needed to raise the temperature of 1 gram of a substance by 1 degree Celsius. Water has a high specific heat of 4.184 joules per gram degree Celsius, and that just means it takes 4.84 joules to raise 1 gram of water 1 degree Celsius. Now, during vaporization, so whenever you boil something and it goes from liquid to steam, heat must be added to overcome those interparticle forces. We know that vaporization is endothermic because we're adding energy. Condensation is exothermic because that moisture hits the window or a person, and all that energy that made it a gas is released onto whatever it is that the steam hits. And that's whenever it forms a liquid. And because of the strong intermolecular forces, water actually absorbs a great deal of heat when it's vaporized. Whenever you sweat and you have the water on your skin, the evaporation actually uses the heat from your body in order to evaporate the moisture, the sweat. And that's why you feel cooler, because your body heat is actually being used to break those bonds and evaporate the sweat. And that's why your body's temperature is regulated whenever you sweat. Now, the specific heat is why water heats up and cools slowly. And this also explains how water serves as a heat reservoir that moderates the temperature of the earth. If you are on a coastal area, for example, the temperatures don't change as much at night. And this is because during the day, water will absorb that heat from the sun. And then at night, whenever the sun has gone down and it's cooler, that heat is slowly released back into the atmosphere. If we didn't have any water to moderate the temperature during the day would be extremely hot, and the nights would be much colder. Now, most of the water isn't pure that we find around the world. It's present in solutions. We have minerals in our water. Even in the tap water that we drink, we have chemicals, from the chlorine that they use to cleanse the water in the water treatment plant. even if you have well water or spring water, that water has minerals from the ground that's dissolved in it. Now, water's really difficult to keep pure because it is such a good solvent. Almost all life-supporting chemical reactions actually occur in an aqueous environment. Your body is like 70% water, so you have several aqueous solutions in your body, primarily blood, and you have lots of different ions and like potassium and sodium, and those are part of a system that helps your muscles and you need your electrolytes to function. So you have so many different chemical reactions going on in your body that it's hard to understand each and every single one. Ionic compounds are soluble in water and they conduct electricity when in solution. So why do ionic compounds dissolve in water? What happens so that they will dissolve in water and covalent compounds struggle dissolving in water? Ionic compounds, we know, have a 3D network of positive and negative ions. So they have really strong ionic bonds. The positive and negative ions then are attracted to the positive and negative dipoles. So here we have our negative dipoles on water. These are from our lone pair of electrons. And so say we have that didn't look very. There we go. Say we have our water molecule here, and we have sodium, which has a plus positive charge, and chloride that has a negative charge. Well, the chloride will be attracted to the hydrogen dipole, which is positive. And then the sodium ion will be attracted to the negative dipole of the oxygen. And the water molecules will surround these ions, which will separate the charged particles in the ionic solid. And that is called dissociation whenever it breaks apart. If it dissociates, the compound breaks apart. So we know that sodium chloride is made out of two particles, and it will break apart into sodium ion and a chloride ion. Calcium chloride will dissociate into three particles, because if we look at calcium chloride, CaCl2, it breaks apart into the calcium 2 plus ion and the chloride ions here. Covalent compounds that contain oxygen or hydrogen have the ability to hydrogen bond with water and thus dissolve in water. So sucrose, which is our table sugar, you can see here, it's got that hydroxyl group, that OH group, and it's got another OH group. And you have some oxygens here that will have some dipoles as well. So sugar is able to dissolve in water. Covalent compounds don't dissociate though. So you have your ionic compounds that dissociate, and they go into their different charges. So they break into charges. But covalent compounds don't have any charge. So they're not going to dissociate in solutions. Instead, you just have a bunch of water molecules that surround your sucrose molecules. I think it's C12H22O11, if I remember correctly. So if you have your sugar molecule, in order to dissolve, the water molecules have to surround each and every sugar molecule to separate it from the other sugar molecules. Covalent compounds don't conduct electricity because they don't have the charges to transfer the electrons. Water does not dissolve everything. There is something, a little saying called like dissolves like. And that just means that dissolving occurs between similar substances. So, for example, compounds being dissolved in water must be ionic. They must have dipoles or they have to have hydrogen bonding. Oil, for example, does not have dipoles or hydrogen bonding and it's not ionic. So it will not dissolve in water at all. So here you have this little meme. Hey y'all, want to hang out? Hey oil, want to hang out? And oil says, I can't mix with you guys. And this water molecule says hydrophobe because hydro means water and a phobia is fearing. So he's saying, you're a hydrophobe because it actually is hydrophobic. It's termed hydrophobic because it oil is repelled by water. So that's a little science joke. All right. I hope you guys have a great day. We'll do more next time.